my great pleasure to be here. Actually, it's my first time in Taiwan, and I really like the culture and the food here. Today I want to talk something maybe exotic or unfamiliar for most of the high-end people here. But if you have any questions and confused about some concept I mentioned, because my background is kind of matter theory, so my language and terminology may be not in a standard high-energy fashion. So please just ask me questions. So the purpose is that I try to propose some simple picture that assuming fundamental lepton and quark can be further divided into some even more fundamental objects, so-called topological Majorana Real mode. And then in such kind of picture, there's a natural way to explain the origin of three generations of neutrinos and their mass mixing. So the Majorana mode recently has been discovered in some nanowire lab. And here is some cartoon that the four-component Majorana fermion actually can be decomposed into. Yeah, so the basic idea is that this four Majorana zero mode can be kind of fundamental structure of Majorana fermion. At long wavelengths, we think that the whole thing is kind of like a point-like particle. But if we really go to the Planck scale, then it's not really point-like. There's a kind of fine structure there. So we know that this neutrino is kind of a deep puzzle in our universe. Kind of, they have extremely weak interactions with other particles, and almost vanishing mass, and the billions of neutrons surrounding us now. And the ghost hunting scheme, so-called neutrino oscillation, actually is the first experimental evidence showing the existence of three generations of neutrino. And more non-trivial, they have some very particular mass mixing pattern. So before that, let me just briefly introduce what is the meaning of this neutrino mixing process. Because in high energy, we know that we identify three generations of neutrinos via their kind of weak doublets. So, for example, for electron neutrino, it has its kind of corresponding partner. But of course, the mass eigenstate of neutrino does not necessarily to be the same as a weak eigenstate. So, in general, for example, for electron neutrino and muon neutrino, we can assume there's a unitary matrices parameterized by this theta angle. So when we create some neutrino in a reactor source, and when they propagate, they can, in principle, they can evolve and through some particular pattern. And after a certain time and distance, we measure them again. And then, based on this overlap matrix, we can determine this mixing angle theta. Okay, so that's the basic experimental setup to measure this mixing angle. So in general, this mixing will evolve three generations, because we know that in our world there are three generations of neutrinos, and people use different experimental methods to measure these angles. So for example, to measure this 2-3 angle, sometimes we call the atmospheric angle. Through this kind of atmospheric interference technique, people can measure this mixing between mu and core neutrino. And 1-2 angle, we call this solar angle. Basically, we measure this solar neutrino mixing. And most recently, it has been focused on this 1-3 angle in this reactor experiment, for example, in Dirac. And they found that for a long time, people thought this angle very small or even zero. But very recently, it has been shown it's non-zero. And potentially, there's a bigger CP violation angle. So this experiment during the last 10 years turned out to be very extremely exciting, because this mixing angle is not like a random number. It has a particular pattern. And it's very puzzle why the neutrinos can have such kind of strange pattern for their mass mixing Okay, so let me also briefly mention the idea to explain this neutrino mass and their mass mixing pattern. We know that in standard model, neutrino must have zero mass. This is because the neutrino mass term always will break this electroweak gauge symmetry, and it's not allowed in the standard model. So the way to compensate this is that people conjecture that at gap scale, Brown unification scale, there exists a certain called a sterile neutrino, which decouple with the standard model gauge interactions. However, there could be some Dirac mass term between this light neutrino and heavy neutrino. Then, if we assume this heavy neutrino energy scale is the gap scale, and this Dirac mass scale is the kind of 100 GeV, this kind of Higgs energy scale. Then if we diagonalize this mass matrix, it naturally have two eigenstates, M1 and M2. Here I just assume one generation, but you can easily generalize to three generations as well. So M1 turns out on the scale of like 0.1 EV happen to be consistent with the neutrino mass experiment, and M2 typically very high on the Brown unification scale. Okay, so this kind of story is very nice, and people kind of well accepted for such kind of principle. But still, we have a puzzle that where does the heavy neutrino mass come from? Looks like there's no reason why it has a very big mass at Planck scale. And also, how to explain the experimental mass mixing texture from a simple principle at the leading order. In the leading order, we mean that, for example, like we assume the θ13 angle equal to 0, and there's no CP violation, but then by turning on quantum fluctuation, maybe we can explain this more detailed pattern. Okay, so here in this talk, we also assume the mass and mass mixing of light neutrinos indeed through this seesaw method, because so far there are no other good method to explain this neutrino mass in a relatively natural way. So the seesaw method seems to be very natural. But in this way, we must assume this neutrino actually are Majorana particle, not Dirac particle, because the existence of Majorana mass. For Dirac particle, this Majorana mass term must vanish. Okay, so let me also briefly mention the history of the this Majorana fermion. So actually, it's a particular kind of representation of the Dirac equation. Namely, if we choose all these gamma matrix to be real, then we can write down some Dirac equation in terms of real gamma matrix and real spinor, which is first proposed by Majorana, who disappeared like 80 years ago. Very mystery. So just as mystery as the Majorana neutrino, maybe. Okay. So neutrinos are very promising candidates for this kind of Majorana particle. But still, there's no natural reason to explain why there are three generations, and where do this mystery mixing angle comes from. So today, I try to understand the origin of neutrino mass, three generation, and compute their mass mixing matrix by investigating the topological nature of Majorana particle. So I will explain in detail later. And now, from now on, I want to refer topological Majorana fermion formed by four Majorana modes as a Majorana ghost. So as I explained at the beginning of the talk, it's a real kind of four-component Majorana field. So in terms of classical picture or in kind of matter picture, you can think about they kind of just like 4-degree freedoms at some fundamental scale. Yeah. So in quantum field theory, we kind of formally write down some four-component spinor. But if you really make a lattice regulation, you can think about, or in some classical sense, it's really a kind of four orbits in a unit cell. So each unit cell will correspond to a space-time spatial position in long distance. So that's the idea that why we need four Majorana modes, because the spinor representation is four-dimensional representation in 3+1b. Okay. So of course we want to ask the question why we want to introduce this topological Majorana modes. So there are several reasons that this topological idea might be promising, because standard model cannot be served as a UV complete theory. We need a lot of fine-tuning, almost 20 parameters to determine this standard model. And also there's no natural explanation of this regeneration, and particularly there's no explanation of why these 1, 2, 3 gauge fields come from. And even we postpone this problem to the ground unification theory, it's still unnatural why we have SO10 or SU5 gauge theory. Okay, so on the other hand, the topological objects can be further, cannot be further divided. So they are very naturally served as a fundamental block of our universe. Actually, 200 years ago, Lord Kelvin conjectured that atoms are topological distinguished vortex ring. You can think about just like a smoking ring, and they linking in some particular way. And the periodic tables correspond to different way of linking. So this idea is very attractive, but of course, it turns out to be wrong. And now we know that atoms are actually made by quarks and leptons. But however, the problem is still there. We can still ask leptons and quark, their ultimate fundamental, or they can be further divided. So there are different ways to think about this problem. In string theory, people want to think about their different vibration mode of a string. But alternatively, here I want to just assume they can be further divided into some even more fundamental objects, the so-called Majorana zero mode. Okay, so in lower dimensions, for example, 2 plus 1D and 1 plus 1D, we also have a very good understanding of quantum gravity theory. For example, in 2 plus 1D, Witten shows that quantum gravity theory can be formulated as this SU2 level K-7 theory. And this quantum gravity really have topological feature. And also, this coordinate reparameterization invariance is essentially a topological invariance. For example, in 2D, if you count in the genus of the manifold, it's invariant under this diffeomorphism or this coordinate reparameterizations. And the essential property of a manifold is actually the chain class. So you cannot change those kind of topological quantum numbers through coordinate transformation. And also, on the other hand, for example, in 2 plus 1D, we are familiar about this topological quantum field theory because the presence of fractional quantum Hall states in quantum symmetry. And we know the source of a TQFT must be a topological quasi-particle. For example, they could be roughly annual. And so we can just conjecture that all the mapped fields have a topological origination in this sense, and all the gauge fields might be just collective motions of those mapped fields. Okay, so this is some basic philosophy or idea to introduce this topological Majorana zero mode. And let me also give you some very simple example to explain what is a topological Majorana zero mode. And the minimum model actually turns out to be extremely simple. We just think about some one-dimensional lattice model. It's a one-dimensional chain. So on each side, there are a pair of Majorana operators. So there's gamma I and gamma I prime. They naturally satisfy this Clifford algebra. So they have the commutating relation, gamma I and gamma J. They are anti-commute, so they are not on the same side. And gamma I prime, gamma J prime, they always anti-commute. So it's a very simple Clifford algebra. And basically, if we have a pair of this so-called Majorana operator, which are generated of Clifford algebra, we can make this electron operator. And in terms of this standard 4 basis electron operator, this model just a very simple superconductor. But this model, sometimes in condensed matter, we call the P plus IP superconductor because this pairing symmetry have a particular kind of pattern. It's not the usual S-wave superconductor. And so in such a way, if you solve this model exactly, you will find there are some dangling mode on the edge. So we call it Majorana zero mode. So you can see it's very easy to solve this model because this gamma I prime, gamma I, is just like yeah, it's basically just like a fermion parity operator, so have eigenvalue plus minus 1. And on each link, these operators they actually commute. So you can solve this model exactly. And once you solve this model, you can still see that on the open chain, there's unpaired this Majorana operator. And this unpaired Majorana operator turns out to be stable on the arbitrary local perturbation. So you can never split this degeneracy on this boundary. And in a nano lab, people actually can realize such kind of Majorana chain now. And the interesting point is that each end is actually half degree operator. So it's kind of further fractionalization of a fermion. In some sense, we call it half fermion. And such kind of things also exist in 2 plus 1D. For example, in a 2 plus 1D P plus IP topological superconductor, you can just create some vortex. And in each vortex, there also will be a single Majorana zero mode. So in this sense, we can also call this vortex as kind of half degree freedom. Okay, so the major concept is that if we start from like some normal fermion, lepton or quark, we can further cut it into half degree of freedom. So we call it Majorana zero mode here.
So are those the two examples in 3 plus 1 or 2 plus 1?
Yeah, these two are examples in 1 plus 1D, 2 plus 1D, but in 3 plus 1D, you can also make a similar example. But there are some subtle things. You always need some string that confine this pair. So in 3 plus 1D, this Majorana zero mode always appears in pairs, not a single one. So that's the difference. I will explain later. Okay, so yeah, so that's some strange thing that might happen in Majorana's wonderland. This is some kind of interesting story. Actually, I copied from a book of this Alice's experience in a wonderland. So it's strange in the sense that it kind of like we discover this standard model. At the beginning, we think about why we have this standard model. It's so strange and not so natural. But on the other hand, in future, if we have a complete understanding about these fundamental objects of our world, maybe this Majorana mode can be very natural building block. They are not something so surprise, and even much simpler than the standard model contents of particles. So that's the idea of this Majorana's wonderland. Okay, so let's start our journey to this wonderland. And the first thing I want to tell you is that these Majorana modes actually carry very strange time reversal symmetry. We know that in a fundamental high energy theory, it's easy to argue that time reversal symmetry must be restored at quantum gravity level because it's a local symmetry. It's a parameterization of the coordinate system. Although in standard model we don't have this time reversal symmetry, but it can be attributed to the spontaneous symmetry breaking as a dynamic effect. So here I assume this time reversal symmetry is fundamentally important, and we need to discuss this time reversal symmetry property for a pair of Majorana zero mode. So we know that boson is kind of very trivial representation of the time reversal symmetry, which is just a complex conjugate. And the fermion is slightly non-trivial because it's like a half boson. So it should carry this essentially projective representation of time reversal symmetry. So the idea is that this fermion actually kind of carries spin up and down, and it forms this prime doublets. So that's why it's T squared minus 1. But actually, if we have a pair of Majorana modes, I will show you that it's even more strange. It carries this T2 cortically minus 1 time reversal symmetry. And the reason why we can have such kind of strange time reversal symmetry, just because this time reversal symmetry action on this pair of Majorana zero mode will change the fermion parity. So in some simple word, you can think about I construct some complex fermion operator out of 2 Majorana zero mode. And then I can define a vacuum of this creation operator, which kind of annihilated by the C operator. And I also can define another state, which is the one particle state. So there are the Hilbert space like a 2 dimension. But this time reversal symmetry, I will show you it must be 2 two-dimensional representation. So it will map this 0 to 1, and also will map 1 to 0. So in some sense that the time reversal operator is really like a super operator. It changes this Feynman parity, and it makes such kind of very strange property of this time reversal symmetry. So the proof is very simple, but I want to, before going into the detailed proof, I just give you some kind of idea about this symmetry fractionalizations in condensed matter system, which we realized turns out to be very universal and very interesting. So the simple example for this symmetry fractionalization is the spin-1 Heisenberg chain. So this model has been studied in condensed matter system for almost more than 20 years, and people know this model pretty well because it's just one-dimensional. But it turns out that this model has a strange property that when we turn on this second term, this U term, so the U term just punishes this energy of this spin-1 configuration because it's a spin-1 chain, so we have 3-degree freedom locally, namely 1, -1, and 0. So this term basically wants to all the spin in the state SD equals 0. When this term to be infinite, we know it's a trivial state, just everywhere it's the state of spin SD equals 0. And when this U equals 0, it turns out this spin-1 chain is still a gapped phase. But this gapped phase is different from the U infinite phase because we always can find a phase transition at U equals 1. So this kind of property signature that the U equals 0 phase might be quite non-trivial, and there are some strange properties there. So in the last few years, actually, we showed that the U equals 0 point, it's a non-trivial so-called symmetry protected topological phase, which means if we impose certain global symmetry like time reversal spin rotation, it's distinguishable from the trivial U equals infinite phase. And such kind of concept we call the symmetry fractionalization. So it's the simplest example of topological phases in 1+1. And we can also show that such kind of symmetry protected topological phases exhausted all the possible topological orders in 1+1. And the physical picture is pretty simple. Suppose we're doing some like renormalization scheme, and we cross-graining the system. And in the RG fixed point, it turns out if we're preserving time reversal or SO3 symmetry, there will be 4 states on a single site. So why is 4? Because the original model we only have this spin-1 sector. But in the cross-graining, we can introduce more and more spin representations. And it turns out in the fixed point, there will be some emergent spin-0 sector. Because if we add this spin-0 and spin-1 representation, we can represent it by 2 spin-1 half degree freedom. So each sublattice actually is a spin-1 half degree of freedom. So in such a very simple picture, we know that on this end, we can have this spin-1 half objects emerge. Although in the bulk model, we only have spin-1 objects. So that's the simplest concept of symmetry fractionalization. And if we impose some time reversal symmetry to protect this Haldane phase, and it can be proved that on the boundary, the system always will have t² minus 1 projective representation, which is spin-1 half. So it's such kind of time reversal symmetry is the same as the time reversal symmetry carried by a relativistic fermion. Okay, so this kind of symmetry fractionalization can be generalized into arbitrary dimension and evolve this group of cohomologous kind of theory. But I don't want to go further for this kind of complications. But let me just switch back to this Fermion model we are interested in. So in the beginning, I showed that a single Majorana chain will carry a single Majorana mode on its end, so which represents a half degree freedom. But now we do a little bit more. We want to impose time reversal symmetry as well. So once we impose time reversal symmetry, a single Majorana chain is not enough. We must make 2 copies of them. And to make these 2 copies of them, it turns out the whole system become new types of symmetry protected topological superconductor. Sometimes we call it D3 class. So the Hamiltonian is still very simple, just kind of Hamiltonian sum of 2 spin because each of chain they are exactly solvable. So the whole model is still exactly solvable. So looks like there's nothing new here. But the interesting question is that what's the time reversal symmetry carried by this pair of boundary Majorana zero mode? Because if we only have one Majorana zero mode, there's no way to discuss this time reversal symmetry, right? So if we want to discuss time reversal symmetry, we must have a pair. And also, we can just do some very simple algebraic calculation. It's easy to see that because this this kind of complex electron operator transform on the time reversal in this kind of familiar way. We map C up to minus C down and C down to C up. So it's not a surprise this real Majorana operator also must transform in the same way because it's just linear combinations of the complex Fermi operator, just linear combination of this real Fermi operator. Okay, so we can think about such kind of representation on the operator. And we can also imagine that the time reversal symmetry on this pair of Majorana zero mode is nothing but just this usual parameter doublets, which namely this T just the UK. So U is the I sigma Y, the usual I times Pauli matrix. But such kind of conjecture turns out to be wrong because this kind of pair is kind of kind of fractionalized degree freedom because on each box side there are always two pairs, not only one pair. So if we have one pair carry this T squared with minus 1 time reversal symmetry, two pair will turn out to be T squared with 1. So which is inconsistent with the original symmetry we want to assign for this topological superconductor. Because for the topological superconductor, we have a kind of C up complex fermion and C down complex fermion, which have a Fock space structure on each single side. So in this Fock space, the time reversal symmetry realized in this T squared with minus 1. So it's not plus 1, right? Because this kind of algebra. Okay, then it turns out that this T operator is incorrect if we want to act on this pair of Majorana zero mode. Although it's correct on this complex fermion, it's incorrect on the real fermion. But of course, there's no doubt that we must let this time reversal operator to produce this kind of algebra. But then the only possibility is that we can design some different time reversal operator such that they still form this algebra, but they also satisfy the condition that the two pair will satisfy this kind of algebra. Okay, so such kind of time reversal representation is possible in the sense that we can actually prove it exists. Because in condensed matter, we have some powerful method that we can map a fermion system into a boson system. And after such kind of mapping, we will show that for this boson system, it have enhanced symmetry. Because we must also take this fermion parity symmetry into account. So if we look at about this local Fock space, basically we have this fermion parity odd sector transform like T squared to minus 1. But for this two bosonic sector, they transform like T squared to plus 1. So the conclusion is that if we also take this fermion parity symmetry into account, the total symmetry we are interested in actually is not a Z2 symmetry, it's a Z4 anti-unitary symmetry, which involves 4 group elements. So the T squared is nothing, just the fermion parity. Okay, so once we formulate in such a way, we can prove the projective representation of such a symmetry turns out to be T squared with minus 1. So this is kind of proof in principle the existence of such kind of strange time reversal symmetry. Okay, so now we can also write down the explicit operator expression for such kind of time reversal symmetry. Namely, this U is kind of very strange pi over 4. It's called a pi over 4 circuits sometimes in the context of quantum information language. So basically, this is kind of unitary operator. So you can easily examine that if